this module, we will learn about the applications of internal energy of a system. When a change in the state of a system occurs, energy is transferred either to or from the surroundings. This energy may be transferred as heat or mechanical work. In thermodynamics, the only type of work generally considered is the work done in expansion or compression of a gas. This is known as pressure volume work or PV work. Let us understand this better with an example. Consider a cylinder filled with 1 mole of an ideal gas and fitted with a frictionless piston. Let's say the area of the cross-section of the cylinder is A square centimeter. The pressure of the gas inside the cylinder is P, and the volume of the gas inside the cylinder is VI. Here, VI stands for the initial volume of the gas. Now, let's apply external pressure PEX on the piston. If the external pressure PEX is greater than the internal pressure P, then the piston moves inwards until the pressure P inside the cylinder becomes equal to the external pressure PEX. Let this change be achieved in a single step. At this stage, the final volume of the system is represented by Vf, and the distance that the piston is moved is represented by L. Thus, the change in the volume, that is, final volume Vf minus initial volume Vi, is distance L multiplied by area A. We know that pressure equals force divided by area. Hence, the applied force F on the piston equals pressure multiplied by area. That is, the applied force F equals external pressure PEX multiplied by the area of cross-section A. If W is the work done on the system by the movement of the piston, then work equals force multiplied by distance. But force equals external pressure, that is, PEX multiplied by area of cross-section A. Substituting the value of force in the equation for work, we get work is equal to external pressure PEX multiplied by area A multiplied by distance L. But distance L multiplied by area A gives change in volume delta V. On substituting, we get work equals external pressure PEX multiplied by minus change in volume delta V. That is, work is equal to minus external pressure PEX multiplied by final volume Vf minus initial volume Vi. The negative sign is added in the expression to obtain the conventional sign for W. According to the latest SI conventions, W is taken as positive if work is done on the system, that is, the work of compression, and W is taken as negative if the work is done by the system, that is, the work of expansion. Therefore, the general expression for work done is written as W equals minus external pressure PEX multiplied by change in volume delta V, which is equal to minus external pressure PEX multiplied by final volume Vf minus initial volume Vi. The expression of work applies for both expansion and compression of a gas. If the gas expands, Vf will be greater than Vi. Then, we can say that work is done by the system. Hence, the value of work done will be negative. Similarly, if the gas compresses, Vf will be lesser than Vi. On substituting the values of volume in the equation of work, we get a negative volume. When this negative value is multiplied with the negative external pressure, the resultant work is positive. Then we can say that work is done on the system. If the pressure is not constant and changes in finite numbers of steps for every stage of compression, then the work done is calculated as W equals minus the summation of pressure multiplied by change in volume. When these values are plotted on a graph, the work done on the gas is visible in the shaded area. However, if the pressure is not constant and varies such that it is always infinitesimally greater than the pressure of the gas at each stage of compression, the volume decreases by an infinitesimal amount dV. Then, work is equal to minus F integral of external pressure Pex multiplied by infinitesimal change in volume dV. If gas expands, then the external pressure is always less than the pressure of the system. Thus, Pex at each stage is equal to the difference between the internal pressure P and infinitesimal change in pressure of the system dP. If gas is compressed, then the external pressure is always greater than the pressure of the system. Thus, the Pex at each stage is equal to the sum of the internal pressure P and infinitesimal change in pressure dP. Therefore, external pressure applied on a system is expressed as external pressure equals internal pressure plus or minus infinitesimal change in the pressure of the system. This is known as reversible process. Thus, a reversible process is one that takes place infinitesimally slowly and the direction of which at any point can be reversed by an infinitesimal change in the state of the system. In a reversible process, the system is in equilibrium in the initial, final, and all intermediate stages. To understand this, let's assume that there is a cylinder with a frictionless piston. Now, let's place few grains of sand above the piston and allow the gas to compress by adding 1 grain of sand at a time. Here, the process is so slow that it can be easily reversed by removing 1 grain of sand at any time. This is known as reversible process. Processes which are not reversible are known as irreversible processes. Under reversible conditions, the relationship between work and internal pressure is written as reversible work equals minus integral of external pressure Pex with respect to infinitesimal change in volume dV. We know that external pressure Pex equals internal pressure P in plus or minus infinitesimal change in pressure of the system dP. Thus, on substituting the values, we get the equation reversible work equals minus integral of internal pressure P in plus or minus infinitesimal change in pressure of the system dP multiplied by infinitesimal change in volume dV. As change in the pressure and volume are infinitesimally small, their product is still smaller. Therefore, the product of infinitesimal change in pressure dP and infinitesimal change in volume dV can be neglected. Hence, the final equation is reversible work equals negative integral of P in multiplied by infinitesimal change in volume dV. Now, if we represent pressure of the gas P in terms of the ideal gas equation, then we get PV equals nRT or P equals nRT divided by V. On substituting the value of P at constant temperature in the reversible work equation, we get reversible work equals minus integral of nRT multiplied by infinitesimal change in volume dV by V. Integrating and applying limits as Vi for initial volume and Vf for final volume, we get reversible work W rev is equal to minus nRT ln final volume Vf divided by initial volume Vi. On converting natural logarithm to base 10, we get reversible work W rev equals minus 2.303 nRT log Vf by Vi. If the gas expands in vacuum, external pressure Pex being 0 in the expression W is equal to minus Pex multiplied by delta V, W becomes 0. This is known as free expansion. No work is done during the free expansion of an ideal gas, whether the process is reversible or irreversible. We know that according to the first law of thermodynamics, the change in internal energy is represented as delta U equals Q plus W. On substituting the value of W in the above equation, we get delta U equals Q plus minus Pex multiplied by delta V. If the process is carried out at constant volume, delta V is 0. Therefore, work done is also 0. Hence, at constant volume, delta U equals QV, where QV is heat supplied at constant volume. You have now reached the end of this module. In this module, you learned that thermodynamics is concerned with mechanical work, also known as pressure-volume work. The expression of pressure-volume work is written as W is equal to minus Pex delta V. A reversible process is one that takes place infinitesimally slowly and the direction of which at any point can be reversed by an infinitesimal change in the state of the system. In a reversible process, the system is in equilibrium in the initial, final, and all intermediate stages. Reversible work W rev equals minus 2.303 nRT log Vf by Vi. If the process is carried out at constant volume, delta V is 0. No work is done during free expansion and change in internal energy equals the heat supplied.